Hi everyone. I will present my research on the modeling of porous structures by using variable order fractional calculus. First, a brief overview of the presentation. I will begin with the motivation behind studying porous solids and then proceed to discuss the physics of deformation of porous solids. By using this discussion, I will show how variable order fractional operators emerge naturally in modeling the response of porous solids, and then I will discuss briefly what is variable order fractional calculus and some features of the variable order non-local continuum model before proceeding to present its applications to the simulation of porous beams. Finally, my conclusions from this study. Porous materials, as everyone knows, has a long and distinguished history of applications in engineering, science, and medicine. Porous architecture is pervasive in nature and found particularly in applications that require the simultaneous achievement of low weight and high stiffness, a concept known as high specific stiffness. We can see several examples in nature of the use of porous structures. For example, animal bones, plant tissue such as bamboo, which we know has a hierarchical porous structure, and then wood and marine shells. Now, the discovery and design of materials with high specific stiffness has been a major pursuit of engineering science. So, it would appear logical to make use of the extensive use of porous architecture in practical applications by learning from nature. Nature inspired porous designs. So, however, this concept of application has faced several theoretical and technical challenges over the years. While the technical limitations which primarily concern the manufacturing of porous solids has been erased over the years, if you will, by the development of advanced and additive manufacturing techniques, tech theoretical challenges still remain. Now, in regards to the theoretical challenges, several studies have shown that size effects play a prominent role in determining the macroscopic multi-scale response of porous structures. Now, in this regard, there is a lack of understanding of how the porous microstructure in general gives rise to the size effects or the non-local effects, and what is the impact of these non-local effects on the macroscopic response of the porous solids. Now, in this regard, existing models face two major limitations which require an implicit trade-off between the accuracy and the computational efficiency. Proper accuracy For proper accuracy, we need complete resolution of the porous solids, which results in computationally prohibitive resources, while models which are computationally efficient do not have the ability to appropriately resolve the interplay between size effects, the porous configuration, and consequently they do not capture fully the impact of the size effects. Now, in this study, we attempt to address these theoretical limitations because addressing these theoretical limitations can enable the design of engineered porosity materials and effect a significant leap forward in many applications, such as, for example, batteries, lightweight transportation, and even biomedical implants. Now, in order to develop a model which accurately characterizes the size effects in porous solids, we first attempt to understand the physics of deformation of porous solids. For this purpose, we segment the pores into spherical inclusions which are dispersed in the bulk in this fashion. Now, these spherical inclusions interact with each other via long-range interactions. This concept can be easily visualized by taking the example of a solid with only two inclusions, where the change in the shape of a single inclusion due to external forces will cause a change in the shape of the other isolated inclusion by the principle of action at a distance. Now one can visualize the porous solid as a network of spherical inclusions which interact with each other in a non-local fashion. Now it is also important to note that these non-local interactions carry a position dependent signature. In order to understand this, we simulated a series of 2D inclusions and observed that the strength of these inclusions decay in a power law fashion and exhibits a position dependent strength. That is, inclusions of larger size and spatial locations with a higher concentration of inclusions leads to a higher strength of non-local effects. Now, in order to find a mathematical expression to characterize this phenomenon, we constructed a 1D lattice with non-local connections embedded with this power law decay and the position dependent strength in the lumped stiffnesses, of course. So when we obtained the 1D continuum limit of this lattice, we noted that the stress uh, in the stress expression, variable order fractional derivatives appear naturally. I want to emphasize that this appearance of variable order fractional derivatives is not merely a mathematical expedient, but is an intrinsic expression of the physical signature of the porous microstructure on the macroscopic deformation state of the porous solid. Now, I assume that the crowd is not exposed to variable order fractional calculus, so I decided to briefly review a variable order fractional calculus. So, fractional calculus is the calculus of integrals and derivatives of arbitrary order. So, instead of having having a natural number as the order of integration or differentiation, we have a fractional order. So, several definitions of fractional calculus exist in this study. We use the Caputo definition. So if we zoom into this definition, we can see that fractional derivatives contain the convolution of a local information over a memory interval with an attenuation kernel. So left-handed derivatives to basically capture the information which lies behind of a point, and right-handed derivatives will capture the information which lies ahead of the point. This imparts fractional derivatives with a non-local character, and upon extending this fractional order to a function, we recover what is known as variable order fractional calculus. The resulting formalism is very powerful and is able to capture evolutionary phenomena in both space and time. A detailed review of variable order fractional calculus and their applications can be found in our study, which is provided here. In this study, in the context of the present study, we leveraged variable order fractional operators to embed the non-local interaction and their position dependent strength in the strain definition. So basically, the power law kernel captures the non-local information, and the varying exponent, which is the variable order, captures the position dependent strength of the interactions in the porous solid. Now, using the variable order continuum, variable order fractional calculus, we developed the variable order continuum model by extending the 1D definition of the strain. Uh, and by using thermodynamic balance principles, we derived the stress definition. Now, before proceeding further, I want to highlight that the note that the non-locality is embedded in the strain displacement relation. So this can be classified as a type of displacement driven approach, and we use this approach because first of all it appears naturally from the continuation procedure, and second it is positive definite, well posed and thermodynamically consistent, leading to consistent predictions. The details of this model can be found in our paper. Now we use the variable order continuum model to respond the simulation to simulate the response of three different porous beams with increasing order of overall porosity. Now, in order to apply the variable order continuum model, it is critical that we first find the variable order which characterizes the different beams. For this, we first obtain the linear response of the porous beams, which requires significantly lower computational time and resources, and then we embedded it within a machine learning framework which learns the variable order linear theory and provides us the variable order distribution. In brief, it takes as input the response, the linear response of any solid, and gives us the variable order distribution which characterizes the solid. And then we simulated the response of the porous beams using three approaches. First, we simulated it using 3D finite element method using the commercial software COMSOL, which fully resolves the geometry and provides us with a reference solution. Then we also simulated it with the variable order model to validate the model, and we also simulated it with using an integer order model using the rule of mixtures theory to highlight the limitations of integer order mechanics. Now this is the response of the porous beams which we obtained from the analysis I mentioned previously. So we compared the average response and as well as the global for a global comparison, and we also compared the geometric response the response of the geometric center for a more strong comparison. Further, we also compared the full field deformation field. As you can see, the variable order model is highly accurate, as also reflected in the error. So the solid lines over here correspond to the error in the variable order approach, while the dotted lines correspond to the error in the rule of mixtures approach. As we move ahead and further compare the performance, we note that the variable order model requires significantly less time when compared to the fully resolved fund element model. Note also that while we simulated the mm, variable order on a personal computer with 8 GB RAM, the COMSOL model required a cluster with 20 cores and 256 GB RAM, which highlights how powerful and computationally efficient the model is. The variable order model is, suggesting that it is essentially a highly accurate reduced order model, which fully resolves the impact of the porous microstructure on the macroscopic multiscale response of the porous beams. Now, the lower accuracy of the integer order model is expected because integer order mechanics does not capture non-local effects, let alone the position dependent non-local effects. Now, now I would like to conclude my study. So we demonstrated that porous solids exhibit an elaborate position dependent non-local effect which cannot be neglected when we require highly accurate predictions. Now we also developed a variable order continuum theory which is capable of capturing these complex non-local effects. We showed that the variable order model is a reduced order model which is endowed with the fine information of the impact of the microstructure, the porous microstructure on the global multiscale response. Also, this type of multiscale behavior, which is also seen in architecture materials, composites, and metamaterials, can also be simulated by using the variable order model. Finally, I would like to conclude by thanking my advisor, Dr. Fabio Sempalotti, and our funders, DARPA, NSF, and Purdue MA, for the financial support. Thank you.